can't see it, the glare. That says charge over potential, right? The main thing with this is saying that capacitance is really, it's all about the amount of charge you can hold over some potential difference. So there's a plate, it can hold charge, and it holds charge in relation to some potential difference. So it's per potential difference, which is between the plates, right? If I turn another plate here, this would then be 8, right? Area. And now we're talking about the amount of charge. See, charge accumulates here. There's a bunch of little cubes, or should I say, small cube, little tiny cubes. They're all accumulating. And more accumulate as the potential increases. So, hello, Daniel. So this is really important though, because you see, you have to understand that that's what the Farad is, right? Farad. This is equal to, we call it, well, dimension-wise, you can say Coulomb per volt, and that is known as the Farad. Okay, that's the Farad. And let's see. You heard Brenda mention this thing called, hello Ian, nice to see you here. Brenda mentioned this thing called breakdown voltage. So what is breakdown voltage? Let's think about that. So it's to say that if I put so much voltage between these plates, then it would be too much. And if we looked at this from a side view, so here's the side view, this, right? That's the side. Then all the little atoms inside here would begin to get ionized, right? So negative and positive. And you get an induced electric field, right? And this is the direction of this electric field, right? So the total is equal to E minus E induced, isn't it? Right? That makes sense. The total is E, the electric field from the whole capacitor plates, minus the induced electric field in the little particles, little tiny particles. So now what we're saying here is, if we put so much voltage, this is a potential difference. If we put so much here, then this is what happens, the polarization of molecules, that's what happens. And then the air begins to conduct. Ian, did you finish up your sentence? So what that says is that this amount, that how much voltage do you need, how much, some big number, it relies on the dielectric strength, which is a number in your book. But for theoretical understanding, it is to say that you can only put so much charge per potential difference on a capacitor. Right? That's what capacitance is. So if you have, this is 10 microfarads, then this will break down relatively easily compared to, say, 100 microfarads. Yes? So it is to say that C will be less, so therefore it cannot hold as much charge per potential. If you have more capacitance, you can hold more charge, but then the breakdown voltage will be different. So that's what breakdown voltage is. It's kind of, you can get asked this on the exam. I think so. So just understand that you would have to be given these, quantities. There's a number in chapter 26 that David showed me this light. Let me try to look for what number that was. It was a very good question. Very annoying question. Oh yes, 55 is a very good question. I don't know if you've tried it yet. It's a good question. And what was it? 40. There's another problem. But anyways, let me see if I can find it. It was a very good problem. I had a diagram too. I'm trying to look for it. Number 48. Let's look at number 48. I'll leave this up here. Okay, so it says each capacitor in the combination shown in the figure that I'm going to draw has a breakdown voltage of 15 volts, 1.5. So you can say BD, breakdown voltage, or you can do delta V as well, that's fine. And it says, here is the circuit. Okay. Okay, here's the circuit. So, what would you say? Parallel? Yes. Parallel? And then series? Yes. Okay. That should be pretty straightforward. But there's a trick to this problem. There's an interesting idea, and there's a trick. So let's look at this. So, yes, you combine these two parallel. So let's redraw that. Parallel means just add. And then this 10. And it's 40 again. Okay, so what this problem asks now is it's saying what is the breakdown voltage of the combination? So they want to know of this combination. We've reduced here to here. They want to know what is the breakdown voltage. This is tricky because remember what I said about breakdown voltage is it relies on the capacitance. How much charge per potential can you hold on the plate, the capacitor. So if you have a less capacitor, a little weaker, then that's going to break down first before these two do. Does that make sense? Because this is 40, this is 40, so they will break down at the same time. Or yeah, they all have same charge Q because series. But what we have to analyze here is if this is the breakdown voltage for the entire circuit, then which one of these breaks down first, and then which follow. That's important. So what you find is that if this is the breakdown voltage, what that's saying is 15 volts sparks, sparks fly. So, what we talked about earlier, electric field, ionization, air, all that. So that's the voltage that this one in the middle is going to experience and break down at. So let me write that. They all have same Q, right? But they have different C. They have different C value. So that will change our value of V. So Q. Let's say this is Q1, Q2, Q3. But we all know that these are all equal. But I'm just labeling them. So Q1 is C2, which is 10 microfarad, and then times delta V, which is this. So it's 10 microfarad, and then times 15 volts. So this has to be the max charge, right? So 10 and 15 should be 150 microcoulomb. Check me, make sure I'm right. 150 microcoulomb. So if this is the max charge, but these capacitance are different than this one, then will the voltage change? Yes. So then now Q1 is Q3, right? So I can just do one solution and it's the same solution. Okay. So Q1 is equal to C1 and delta V. But this time I don't know the delta V. I'm looking for delta V. The reason is because this is the max charge. Q has to stay the same. So if I found Q for Q2, then I have to know that this is the max amount of charge that has to get applied to the whole circuit. So that is what this Q1 is. So then we say 150 microcoulomb divided by, what is C1? 40 microfarad is equal to delta NV. And then, and check me, make sure 3.5 volts should be. So it is to say that 3.5 volts is where the 40 microfarad capacitors break down at. The 10 microfarad breaks down at 15 volts, and the 40 microfarad capacitors break down at 3.5 volts. This is the total maximum voltage that it can break down at. But because these capacitors have more capacity, more charge over the potential, then it will take less potential to break them down. There you go. So the answer to this problem is adding up the breakdown voltage of the 10, the 40, and the 40. So we just say like V total, or so go 3.5 plus 15 plus 3.5, which is 22. Yep. Pretty good problem. I like it. Do you guys have any specific problems you want to go over? Because otherwise, I'm just gonna probably, just go over the basics, whatever we need to go over. I know Daniel needs a little help. Ian, if you have a question, let me know. If you want me to go over. Yeah, that's a bit tricky. To reduce it down to a series arrangement. See, the reason why I found it hard to initially grasp this problem as well, in terms of why did we break it down to series and not just down to one capacitor, right? And then find the C equivalent and do the breakdown voltage. Why did we do that? And the reason being is because we have to acknowledge the fact. So we must acknowledge the fact that each of these has an amount of charge per potential. That's the whole thing about this that really comes back to the very first page of this chapter, the very first page, that capacitance is an amount of charge per potential that these plates can store. So it is to say that if you have a larger capacitor, you can hold more charge per potential. And when we're looking at charge and we're figuring out how much of it is there to create potential difference, right? There's charges accumulated here and here, and it creates the potential difference, all those things. So, how much of it can we store? If we have a bigger capacitor, we can store more of all this and make it greater potential. So that greater potential, if they say to us that the breakdown voltage is 15 volts, then we have to understand that 15 volts is applied across each of these capacitors in a different way, because some of these capacitors can hold more charge per potential than others. So what you'll understand in the next section, this kind of connects. You'll understand 27, and then you'll get this a little bit more, because we'll start to talk about current, and we'll start to talk about how it's the same rules of how potential is divided like this, and charge the same, current the same, but there's an underlying feature that shows you how does the voltage vary, as a function, like a sine function, in accordance with the potential. So, how does potential vary with charge as a as a sine function. And when we start to see that, then you'll realize that, because these are greater capacitance, they actually get less voltage to break them down because of this relationship. V is inversely proportional to C, so then therefore that says greater C, less V. Greater C, less V. Does that kind of make sense? Hope that kind of makes sense. Let's see. This is kind of cool. It was hard to start up in YouTube. I was really like, how do I do this? I haven't done this since I was like middle school. I used to make like anime videos. Yeah. Oh well. Let's see. How about? Let's see. You guys want to do some dielectrics? I like dielectrics. Daniel, are you ready? Are you ready for dielectrics? Can we do dielectrics? Okay, I'm gonna erase all this. Oh, how to get the charge. Yeah. I say we ask Brenda about that question. It's a really good question. Seriously, number 48. Very, very good question. I'm going to do some quick rundowns with dielectrics for you guys. And then we can get into other stuff. So, one of the key things to know about dielectrics is proportionalities. I find that understanding proportionalities will help you understand why if one increases, then the other decreases, such and so forth, right? So, what is C proportional to? Proportional to D, right? Wait, no. A. And inversely proportional to D. And so these are really important because when we put in a capacitor, or when we put a dielectric in a capacitor, then C becomes proportional to K. Okay. So let's write this out all in the function. Right? So that's how a capacitor changes with dielectric introduced. Another way that I like to show it is, this is really good to remember, because now we can start to dissect what are the other parts of C. How can we change C? So now we can look at other variables. So I'm going to ask you, but maybe I don't know if you can reply quickly on the chat. What's C? What is C? Besides what I've written here, what is C? Is it Q over V? Yeah. Yeah. Okay, so if it's Q over V, then if this follows, right? So now you can see two relationships here, actually. You can see that Q is directly proportional to kappa. So you can say something like this. You can say Q is equal to kappa times Q0. But then you see here that potential is inversely proportional to kappa. So you can say potential is equal to the initial over kappa. There's one more I'm missing. Hello, who's joining? There's one more I can talk about here. I've had charge, potential, capacitance, energy. U. So the U0 over V, or kappa, sorry. I'll show you why. What is U in the capacitor? See. It's also, and it's also, right? Yes? Okay. So I can take any one of these, and I can take any one of those, and I can combine it. So I can say U is equal to, how about this one, and this one? And so I'll say 1/2, and Q and V, and I'm going to replace Q with a dielectric. And it's going to be K, Q, 0. Oh, shit. Wait, no. This could be 0. I don't know why I didn't. Let me see. Eraser. I think I have to use this one. Let me see. C0, C0. Oh, okay, I know why. I did this earlier too. This is interesting. Oh, there's 4 people. Wow, that's cool. So I have to replace both. That's the key here. These are the basic equations for energy and capacitor, but only in a capacitor, right? So you kind of have to now replace both of these with what you know about dielectrics. So let's try that. I think I'll do this one right here. So it's a U is equal to 1/2, and if I replace C with C kappa C0, it's so kappa C0, and then delta V with delta V, V initial over kappa. So what do we get? U is 1/2 K C0 E0 squared over kappa squared. Let's cancel, and we get isn't this the equation here? So then that's saying that energy is inversely proportional to kappa. That's what I said. So these are really, you guys should think about maybe putting these on flashcards or something to remember all these proportionalities. That way, when you think of one, you can imagine the other. If charge changes, you can know potential changes. Or if C changes, A, and all these things, right? So make sure you have your understandings of your relationships. Let's see. I think it's Okay, anybody have dielectrics or insulators? Yeah, that's what we were talking about before, breakdown voltage. So that's when you have a capacitor. I draw it nice and big so we can really look at it. Electric field is this way, yes. Therefore, how are the molecules aligned? If you're having trouble seeing this visually, I suggest you go to 26.7 in the book and go look at those pictures. They're really good pictures. But this is how the atoms look. Because it would like one side of the atom would get polarized due to the positive charge, so it would be negative on the left. And then over here, I have an induced charge as well. So these are called induced electric field. And when you have so much of it, if you have too much, actually, if you have so much electric field flowing through, then guess what happens? The air gets ionized, and then your hair stands up on end, doesn't it? Or isn't it? No? Yeah, right? Okay. So keep that in mind. Think about those things. This is all static electricity. What does static electricity do? Or stand up on end, right? Okay. That's pretty much what's happening here. The air is so rich with electric field. Electric field's just going through that it gets ionized and whoosh, sparks. All sparks fly off. That's what's called fringing. Oh yeah, that was pretty bad today. She talked about fringing. I don't know if any of you were in the first class. That was a little. You guys want to talk about fringing? It will get covered in the exam. So let's talk about fringing. So you're gonna all tell me electric field is this way, right? But it is observed that the electric field around the edges are like so. And so if we look at the tangent lines, this is electric field. And the tangent line of this, right here. Right? Now Brenda has me confused. Now, hold on. I know that it has to go up and in. So, oh yeah, fringe. Force, electric field. Yeah, okay, I got it. So this is electric field. It's going this way. And this would be the tangent line of that electric field. And this is the line in which the electric field acts along the tangent line. You know, for that little speck. And so this is where the force is then. And so what are the force vectors? Y, X. And same thing here. Where is electric field going? Like this. This is electric field. Tangent. And so this is the force. And And how do we know? Because what they're saying is, oh, now there's only one person. Everybody's like, this is too much. God is teaching way so much. Well, hey, it's good stuff. I would say concept. It's good to know concept. So here, the force is going this, it's going this direction because this is like positively, and this is a negative charge. That's how they look at it. This is a negative charge. That's a positive charge. So if you look at these two, then the resultant vectors are like this. And so only the fx contribute, and that is what is happening is the work is being done, and that's the force in the x direction, and it can be some distance, usually like d by 2, like if the whole thing is d, or if this is all L, then it's usually half. There's a problem in your book that does this. I'll also have you guys look at this problem tomorrow in SI, so don't worry. We'll definitely cover this problem. It's number 65. 65. Yes, it wasn't intuitive, huh? It's like you would think because you're pushing it in, you're giving that force, but actually, yes, it's the electric field that almost, I would like to say we haven't done magnetism yet, but think about a magnet and how as you get closer to it, it wants to either attract or repel. Kind of is the same thing here is when you introduce a body that affects the electric field, then the little atoms will, become partially ionized, or they'll be polarized, right? And so they want to bring it in. The positive wants to be with the negative wants to be with the positive. So it pulls it in. Yeah. This exam question. But if you understand it, like Dr. Brenda says, I think you will do very fine in the second exam, Ian. Good job on the first one, by the way. Very good job. Any other questions you have? Another problem you'd like to go over? I have another 20 minutes, and then I'm going to probably sign off for the night. Dipole moment. Okay, sure. Let's do one of those. You won't get tested on it. However, it's good to know. Conceptually, it's the same understanding of polarization. You understand that the atoms are all randomly associated inside the capacitor, in the air or in the dielectric. So it's the same concept, but now we're looking at the very molecular level. So let's take a look at that. You have electric field here. And I believe so it's like this. They're not necessarily joined, but it's like the distance between them. And we kind of find a zero here. We call this theta. It's our 0 point. And then what we say is that there is a force acting this way, Coulomb force, and a Coulomb force in this direction. We call this distance A. This is also A. So the total distance is 2A. And what they say is that the dipole moment points from negative to positive. So it's a vector. And so if this is the vector of the electric field, and this is the vector of the dipole moment, we then want to say that the torque is equal to the dipole moment across E, and the other one to look at is the energy or the work that is required, which is so same principle, really the same setup and everything, but just two different equations that use both of these vectors in one way or another. Next, we understand that we have to, so this is where you're going to use a right-hand rule. So it's a right-hand rule, and I don't know if you've learned it 250A, you probably have maybe, but this is going to be our X, or this is going to be our Y, and this is going to be the direction of torque. Or another one that we do, and you'll see as Brenda teaches you, and it's the way I do it as well, is instead of having the finger like this, you use just your thumb as X, your fingers as Y, and the palm is normal out, so that's the direction of Z, or torque. So here, I'm going to take my thumb, and it's P cross E. So I have to point my direction, P, the direction of P right here. Then I have to keep my hands in the direction of E, and so it will spin. And what way is that spinning? It's counterclockwise. And that makes sense too, because it makes an angle theta here, and we'd like to decrease theta. Decrease. And then from there, I think it's kind of easy. You usually are given E, and you're given, you find P because you know that P is 2A and Q, so all you need to know is Q, and then plug in everything else, right? So torque would be 2A and Q, and times E, and then times sine of theta. And then for energy, it's pretty much the same thing. The cosine theta, right? And then you just always say that this energy is the work done to move it. And then if she wants to know that, you know, if you're in this configuration, and what is the, how should say it? What is the max potential or maximum work done to get it in the highest position? That would be 180, because then it would have to go all the way around and do a whole pi rotation. But really, the core of this is just about P cross E, making sure you're using one of the rules. Make sure you look at it. You do P, E, and then twist. You'll also see Brenda do that. So make clarifying questions. I know you get it pretty quickly, but just in case, she shows you a way of doing something with your hands and it doesn't make sense, ask her. I always tell everybody, ask as many questions as you can, really. So that's it. I think that's it for dipole moment. Any questions on this? I have another problem I did earlier today. If you'd be intrigued to see it, it's number 55. I found it quite challenging. Let's see. Okay. Let's see. Pretty crazy. For the book, I would say, let me see. Yes, maybe there's a couple YouTube channels that you can use to help you understand the concept. There's two I've recommended that are pretty good. One is by the name of you can search up MIT Martin Lewis, and he has everything from you can go back to torque, or you can understand new physics 222 material as well. And then there's also his name is Michael Van. So if you like van, like the car, let me write it. So those two channels are really good about giving you a really concise rundown on a problem or a concept. The MIT videos are a little longer. They're about 40 to 50 minutes, but they're packed with lots of actual lab experiments and help. So there's lots of good resource there. Aside from, but you will not need it. Like I said, you will not be tested on it on this exam, but the cross product will come back for the third exam. So, okay. Let's see. Go ahead and continue this. Okay, this is a really fun problem. So, this is number 40 or no, 55. And it says this is plate P1, plate P2, plate P3, and plate P4. And that by looking at, they describe it in the problem, but by looking at the diagram, you can see that the negative is connected to P1 and also connected to P3 when the switch is closed. And for here, they have the positive connected to P2 and also when the switch is closed, connected to P4. What they want from us is, first, they say that due to P1, P2, and P3, what is the capacitance? And then they ask for the charge on plate 2. So first the capacitance of these first three, and then the charge on the second plate. Then they ask for all the plates, what is the capacitance? And then what is the charge on the last plate? So the tricky thing here is that these are just one plate. Usually we're used to seeing the circuit and a capacitor like this, but now we have these. So since they're plates and they're charged, there's an electric field. This is positive, this is negative, right? Negative, and this is positive. But for this first part, we're just looking at the first three. They say that the switch is closed down here, but not up here. So just the first three are charged. So if these first three are charged, then the electric field from this one would like to go this way. And would also like to go this way, right? So that capacitance, how can I find the capacitance of these three plates? First, I must remember and recognize that a capacitor is two plates. So it has to take two plates, right, to make a capacitor. So you make a capacitor out of these and out of these. So one of them will be C12 and the other one will be C23 because a pair of them makes a capacitor. There's one here and there's one here. So capacitance of the whole thing is these two, but how are they connected? Parallel or series? Look at the diagram first. Are these two capacitors in parallel or series? They're in parallel because of how they're connected on the wires. They look like they're in series because they're right next to each other. However, looking at the wires and how they're connected by the wires, they're in parallel. A little tricky. The problem also gives us values for A is given, B is also given, and let me see what else is given in this problem. I believe the potential And that is probably it. Yeah, okay. So I'm just going to keep it in terms of variables, easier. C equivalent will be, if these are the same A and the same B, so these are separated all by B, then they are the same capacitance. So it'll just be 2 and say C1, 2, or C, 2C. Or I can just say 2 epsilon A over B. That's the right answer. That's that. Now what is the charge on P2? The charge on P2 is due to both electric fields here and here, right? So we're going to use our C equivalent that we found of this pair of capacitors to find the charge. So then it's going to be Q is C equivalent and 12 volts. So 2 epsilon A over D times 12 volts. Right? And that would be the charge on P2. Okay, now we're going to look for the total capacitance. Now, if I close this switch, what is now the capacitance? Now you need to go back over. And this plate is now charged. So now there's an electric field here. Going like that. So now are there 3 capacitors in parallel? C34, right? So now, what's that C equivalent? Well, if they're all the same C, then just 3C. C2 plus C23 plus C34 equal to 3 epsilon A over E. Last part, I want to know what's the charge on plate 4, so the last plate. What does the plate 4 contribute? It contributes this electric field and only this electric field, just that first one. See, when we looked at the second plate, we saw that the second plate makes 2 electric fields, so it was due to both. It was due to each of these. But for plate 4, it only produces 1 electric field, so it's just going to be equal to Q is equal to, and you can say C34 and delta V. Because it's just going to be, it's not going to be the combination of them like we did on part B. Part B was the combination. This instead now is just the capacitance due to 1. So epsilon A over D 10 times 12 volts. Is that good? Follow? All right. Well, good sir, if you do not have any questions about this problem, I will sign off for tonight and we'll see you in SI tomorrow. Okay. Thanks for being awesome students. everybody that came to the stream, anybody that will watch this later. Thank you. Please remember to share with everybody and subscribe. And remember to send me requests, leave comments in the video, in the comment section of the video, for any questions you want me to go over. And have a good night.